Lecture 34, DevOps Configuration. So this is part one of two, when we're going to talk about DevOps as a topic, and this part, well, is about configuration, because, well, there's setup and then there's execution, and both of those things deserve some mention. So we'll start with the setup part. So far, a lot of the stuff that we have talked about, not exclusively, but close to it, has been a one-off kind of computation. You want to figure out the answer to a question, you write some code to do that, and when you do it, you execute it, it's done. After that, right, we might think about, okay, can we speed up the execution of that particular evaluation? But that's kind of it. It's not necessarily things running for an indefinite period. Course assignments have been like that, right? We've been asked to implement something or improve something that exists. It runs for a finite time, it produces an outcome, and then based on that, we're done. But many systems are really long-running. The phrasing for this is generally available, which is to say that responds to requests whenever it happens to arrive. And that's ideally not surprising at this point. We've spent some time thinking about, say, queuing theory, where we have servers who serve requests, and those servers are sort of generally available, and that's going to just remain the case. So this gets us into the notion of operations, right? Your service or your product, whatever you want to call it, is more likely than ever to have at least some component that's server-side, whether it's hosted in a cloud platform or not, and this server-side component is under your control, and it is something that you hopefully want to keep running. So we're going to talk about using our skills that we already have related to software development in operations, that is system administration, database management, that sort of thing. And it has some relevance because, well, the operations, or IT if you prefer, processes and procedures have a certain amount of similarity to what we're going to do. And it is the case that many companies these days use combined teams that have some development aspect, writing the software, and operations, tending the software, looking after it as it executes. Because, well, the trend today is away from sort of strict separation between the development team and the operations team, running the software and the infrastructure. So it does prevent this sort of works fine in dev ops problem now situation where, shall we say, incentives are poorly aligned. Now, as you can imagine, right, the separation is sort of totally non-existent at your sort of typical startup company. You don't have money to pay for separate development and operations teams. So you don't really have them, right? Like you wouldn't have one person who's dedicated to the idea of doing the operations stuff when it doesn't make sense. So you would just ask the developers to also do the operations part of it. In the beginning, there's really not that many servers, right? There's a demo system, there's a test system, there's your staging environment, whatever it is. It's not a lot, but it spirals out from there. You add more services, you need to tend to them, all of those things. And in this company, given the skills of the people who are involved, I mean, you're not going to ask the salespeople to manage the servers, right? Like, that doesn't make sense. The marketing team isn't going to do it. So you have DevOps, and also sometimes referred to as software reliability engineering. So is this good? Is it bad? Like anything, it's a tool, and tools can be used for both good and evil. And you've got to use it correctly if you want to get the benefits, but there's no force of nature that forces you to use it correctly. It is entirely possible to do everything wrong. There's a lot to be said for letting developers to be involved all across the software development lifecycle, from development to deployment to management to even training a customer on how to use the software. Getting feedback directly from the customer by taking a support call can actually be really interesting. You can really learn a lot doing the operations part. And moreover, it provides a lot of motivation to use proper management and maintenance tools and procedures. When it's you who gets the call when something goes wrong, it certainly increases the likelihood that you are going to care about whether or not a bug has been introduced in the particular thing that you're going to work on, right? If the pain of operations is felt by developers, then they might do something about it, right? If it's a problem of another team, somehow those tickets just never make it to the top of the backlog, do they? But if it affects me, if I'm the one who gets woken up in the middle of the night, my incentive to make sure that we got it right, and that I'm not going to have another miserable night of sleep because the backlog of items to process is really large. The motivation is there, isn't it? Okay. So when we are actually thinking about doing this, one more thing before we go on. As the company grows, you could consider whether a dedicated operations team is preferable, and it might be good to have such a team, but shifting realistically all the workload to the dedicated operations team probably isn't ideal, and it probably isn't scalable. If the operations team has to be involved in everything, they can very quickly become a bottleneck, and everybody's happier, I think, if developers are able to solve their own problems instead of opening tickets and then hassling people to please just do the thing. However, if you have a dedicated operations team, they can be the experts. They can build tooling and guidance and everything that the developers would actually need, so that, well, the ops team doesn't have to do it for them, teaching them to fish as opposed to providing fish. Okay, but to make it work, there are some things, and it seems now like the one I'm going to talk about here, continuous integration, is like, of course, I can't believe we have to say it. It's like saying, oh, you need to breathe to stay alive. But it wasn't always the case. But continuous integration is a best practice that everybody is expecting and should expect to do now. That just means every change or related group of changes is built and tested to evaluate it individually. Once upon a time, that's not what happened. Code changes getting put together didn't happen on every build, nightly or otherwise. It was a weird time when builds were slow and expensive, and you're getting something into the main branch of your software involved asking nicely and bringing somebody a physical disk that they used to copy everything from here to there. Not great, but I think we're past that now, given that we have fairly extensive use of version control and automated testing, good deployments. But the basic plan is you pull the code from version control, you build it, you test it, you report the results, and hypothetically, if everything went well, then this built version is possible to deploy. You may choose to deploy it automatically when it is ready. You may make that a manual operation, or it may be scheduled so that it takes place at some later time. It happens overnight. That kind of thing is very dependent on what problem you're solving and how much downtime, if any, you can reasonably tolerate, and things like that. Usually there is a social convention to not break the build. People usually attend to it quickly if the build is broken, and these things should be sent as a notification on Slack or Teams or email, I suppose, if you prefer, just to let people know when something is broken so that people know what to do and make a good decision about whether we should fix this or whether we should just undo the last changes or do something else. And systems have frequently come with long and complicated configuration options. You can read some stuff about SendMail and Apache and Nginx. But the environment that you're running your code in is also kind of a configuration. If we treat configuration as code, we get much better results than doing anything else, right? It's not enough to just have a wiki page or a GitHub document titled how to install your app. Complicated means mistakes. Asking people to do it manually just doesn't work. So make it automatic. Make it a repeatable, scriptable kind of operation. So version control. You should have version control for your configuration, and it manages your infrastructure and things like that. There should be code reviews on changes to the configuration, just as there are for any other code changes. We should have a way of testing the configuration to verify that it does what it's supposed to do. Do they generate expected files? Do they spawn expected services? And configurations ideally will converge, although they might not terminate because of its indefinitely running service, right? But the service should become available. It should be ready for receiving incoming requests, something like that. We ideally have a suite of modular services that integrate together smoothly, and we have configuration files which we should be able to refactor as is needed when things change. Then we do stuff as needed to keep on top of it. And finally, of course, use continuous builds. We're definitely going to build and execute this configuration whenever it changes to verify that it makes sense, that it does what it's supposed to do. So I'll talk about kind of a specific example, and I'll talk about Terraform. My feelings about Terraform are a little bit mixed. I think it's a good idea, but it has some drawbacks. But its whole purpose is to manage your configuration as code, where you want to run your code using a cloud provider like AWS, and then you can control the infrastructure with Terraform. It is you complete a configuration file, and it's going to, based on the configuration file, create a database for your service and update the network rules and allow these users into the GitHub group that are necessary for working on it. All that kind of stuff you can manage using Terraform and then have that configuration applied very easily. This is quite useful, particularly when we're talking about managing a large number of services and a large number of users. There's no reason why we should have to keep track of that manually. Interestingly, planning is essential. Terraform has a plan operation, and it can verify whatever operation you would like to make. So you've made a change in the configuration file, and you can say Terraform plan, and then you can ask it to do the thing that it's going to do if you're comfortable with that plan. Right? We want to verify that our change is actually what we expect. It's not accidentally deleting a whole bunch of data. It's not accidentally deconfiguring some databases and things like that. And the plan operation also gives you some information about the expected cost. The expected cost is obviously an estimate for these things, but it's not 100% accurate, but an estimate is good. We do want to verify that we're not about to give all of our money to Jeff Bezos. That's probably not a great outcome as far as your company's long-term health is concerned. If you're happy with the change, you can apply it. But I remind you that things can change between plan and apply. So if a significant amount of time has passed between the planning and application, then there is a distinct possibility that we end up doing something we didn't expect to do or overwriting a change that we didn't mean to change. So the plan operation is not perfect, right? Some of the things, like if there's a unique identifier that's going to be generated, it's only known if they're actually created. So it's hard to know what the unique identifier is going to be, and that's okay. However, whatever we do with Terraform, we do have to be careful, right? Non-destructive changes are generally easy to deal with. You just make another PR that corrects it, and once you've planned it and applied it, things are okay. However, there are also destructive changes. And destructive changes are sometimes very difficult to undo. It's easy for bad things to happen with Terraform. You can accidentally tell it that you want to destroy all GitHub groups and it will gladly carry it out. This has the side effect, and this actually happened to me, of causing some people to message you on Slack in a panic, thinking that the removal of their GitHub access is actually a sign that they are being fired. They were not. That's not what happened, but I see why they were worried. Restoring some information in destructive changes might not just be as easy as reverting the change. If I revert the change around the GitHub groups, we'll recreate the groups and re-invite the people and all of that. But If you told your tool to destroy a database, reverting the change may recreate the database, but it doesn't fill in the data, not its contents. So you took backups, right? Right? Okay. Another point about common infrastructure. Now, using tools to manage the infrastructure is important, but we should view different parts of our infrastructure as having a certain interface, and communication should be done exclusively via that interface or API. This reduces the coupling between different components, and as we discussed, helps you to scale the part that need scaling. So that would be important. We should try to avoid, incidentally, this sort of not invented here syndrome. It's usually better to use an existing tool, whether it's open source, commercial, or provided by your cloud platform, than to roll your own. But if you're looking for storage, some sort of access layer, use S3 or a database or something to that effect. For naming and discovery, which is how do we find services and find which services are available, we could use a gateway, or we could use something like Console, which helps us to identify what things are available. For monitoring, there's lots of cool monitoring tools, and we'll talk about some of them in a little bit. Prometheus might be sort of one example of something that we could use. And all of those things are common, right? We're not the only people who have ever had this problem, and in fact, it's something that basically everybody needs. So good tools for this exist, and we should resist the temptation to just make our own, because we think we know exactly what we want. Sometimes, though, what you need is not available, and you're just going to have to make it. With that said, one of the things that I always want to ask when we say, should we make this ourselves, is this what we're best at? Right? Our core competency is X or Y or Z, and are we right now working on something that falls within that core competency, or are we like reinventing an existing service that already exists out there? Right? Like, we might be good at software development, but we don't need to make our own human resources platform, right? We could just use one that exists. There's lots of those. We might be able to build it, but it doesn't mean we're doing what we're best at. I want to also add that you should think extra carefully if you plan to do anything yourself that is security related or otherwise related to authentication, encryption, anything of that nature. I'm going to say that unless you have experts on staff who really know the subject very well, and you're willing to pay for external reviews that focus on auditing the security of the thing that you built, it's probably better not to do it yourself. If you do it yourself, and there are security vulnerabilities, then it's going to be a big problem. You're more likely to end up with a terrible security breach than a terrific secure system. So you have to be kind of careful about that. As a second follow-up point on that, if the tool you're looking for doesn't exist, there might be a reason. The reason maybe is you're the first people to think of it, and okay, good, carry it out, please proceed. But maybe it's actually that the idea isn't as good as it sounds at first glance, either due to inefficiency or maybe just not being that great in principle. So it is important to think twice about these kinds of things before you make them yourselves. With that said, big platforms like AWS are constantly launching new tools that might be exactly what you want, and your best strategy is actually to wait until the managed service is provided for you. You may have to get by without it for at least a little bit longer, but if that is the case, well, listen, patience is rewarded. Right? You can also feel like very frustrated if you spend a lot of time building something, and you're so excited about launching this as a solution, and then like the following day, your cloud provider announces that they're launching a thing that does the exact same thing, and it's a managed instance, and you don't have to configure it and care for it and install software updates on it because it's all done for you. That would suck. it could happen, right? Your feeling of like all your work has been rendered redundant immediately is kind of miserable. And I used to work with somebody who was a manager of a DevOps team, and he said his best strategy in terms of implementing things was just wait, because the cloud provider will implement it for you. Like, all right, I respect that. It's not to say he never implemented anything, but I think he had a point. Let's also talk about naming. So naming is one of the two hard problems in computing, as they say. There are really only two hard things: cache invalidation, naming things, and off by one errors. There are lots of ways to name things, and it is kind of contentious sometimes, right? We have to come up with names for different things that we want to do. It's just going to be necessary, right? We could use names for resources, canonical names for servers, Java package approach where we just use dots to differentiate the various things. Like, that's an option. There's other things we could do. We could assign unique names to different servers. We could use aliases to specify functions. As long as you pick something and you're consistent, that's pretty good. Consistency is the key, right? And if we don't get it right, we just end up frustrating ourselves. Now, here's a real problem that I have really encountered, and it's been kind of a fun debate, as much as this kind of debate can be fun, which is about whether a name should be meaningful or fun. There's a spectrum, of course. There are things that are interesting, and there are things that are not, right? But there's at one end of the spectrum, we choose very boring names. Right? If the service is called billing, well, that's a lot better in helping us identify what it does than if it were called potato, right? But that might actually be more confusing than if it were actually called potato. Because, well, when you say the word billing, do you mean billing as a service? Do you mean billing the team? Or do you mean billing the functionality? That's not necessarily clear depending on context, right? So we're going to have to make some decisions about that kind of thing, and it's not necessarily a slam dunk, who is right in this situation. Similarly, there's also this idea of like, well, if we want to replace the billing service with a new one, is the new service called billing 2? I don't know. All of this presupposes that actually your service does exactly one thing. That's the ideal if you are aiming for some sort of microservices architecture. The goal is that a service should do one particular job, and it should do it well. But sometimes there are related pieces of functionality, right? If billing and accounting go together, should your service be called billing and accounting? Do you rename it? Is accounting just folded into billing, and you just have to know that accounting falls under billing, and that's just the way things are? Like, how do people learn that? It's not easy. There's no magic to it. The other thing that I say is that descriptive names aren't magic. I've seen an example where there's some anonymized teams called X infrastructure and X operations. And I would estimate that about 35% of queries to each team result in a reply says, actually, you should go to the other team. Right? And they've tried as hard as possible to give a very descriptive name that you couldn't possibly confuse with something else, but it's not entirely clear to people sort of what's the difference between the infrastructure and the operations and who's responsible for what. And the problem is not solved by having more descriptive names. It's by having some sort of infrastructure that helps you find what you're looking for, more so than it is any particular name that you could never get wrong. It gets worse also when a team is responsible for a shared component like a library. If this common library is looked after by a specific team, how do you know, right? This common library, it's used by 10 different teams, and one of the teams has been nominated as the people who maintain it. but you don't change the name of the common library to reflect the name of the team that looks after it, do you? That wouldn't make sense. So I think the real solution is like service discovery. It's this idea of a tool with some sort of directory information. Just as an example of something that I've used, ops level is quite helpful in terms of identifying which team is responsible for a specific service and who's on call, and the maturity of the service and everything else that you could ask about it, and that's pretty good. I think other tools exist. They also do more things than this sort of information, but something like ops level is good for helping us find out about the service and also keep on top of it. The other thing that I want to comment on is that there are potential morale implications for insisting on boring names for team and services. There is a reason why a basketball team is called the Toronto Raptors and not the Toronto basketball team, with apologies to FC Toronto. Right, the idea is that there's some identity, there's some branding, there's some element in there that unites the team, that makes it a little bit more interesting, right? Choosing a mythological name or a fictional organization can have some feeling of identity and some team building in there. Avengers Assemble, and fun has a morale impact. All things considered, I think a lot of people would rather work for a company where fun is permitted as opposed to one where it is forbidden. Next note here is about treating servers as cattle and not as pets. Pets are treated as sort of individuals, and everyone is different, but cattle is treated as kind of a big herd. And by servers, we mean actual physical servers, virtual machines, containers, whatever you're actually using. We would like to have reproducible tools for managing them so that the manual intervention is basically zero. At the very least, we want to be able to spin up servers programmatically, so we need more instances of a particular service. We just get it, and we don't have to do anything specifically. We don't have to do anything by hand to make that happen. And as I say, the title here references this idea that we should sort of treat computers as if they are a herd. They're a big group. We get them to move as a group, as opposed to focusing on the individual differences. And to give another example of a tool that I've used in the past for managing infrastructure, we'll talk about Kubernetes. It's used to automate deploying and scaling of applications, so we don't have to manually manage them. If we want to deploy a new version of some container, we just tell the service to do it. And the part about how it does so is it provides a framework. It'll do some load balancing, automatic rollouts and reverts if things goes wrong. It will check the health of instances, replace them if they die. It handles a lot of fun stuff that you would otherwise have to deal with, and you would probably rather not. And we'll also talk about canarying, but not this kind of canary. Rather than deploying everything at once, one way that we can test a deployment is, doing a deployment of some servers, but not all. So when we do this, it's also a form of sort of testing in production. So we deploy the new version alongside the old version, and what we'll do is we will stage for deployment. We're ready to give it a shot. And we will then remove some canaries from service, upgrade them, run some tests, make sure everything went okay with the upgrade, and reintroduce them into service and see how it goes. So if it's good, we keep or increase the fraction of the services that we have updated until we're sure everything is fine. And we're just upgrading some, and it serves some of the traffic, and if everything is okay. Right? Sometimes you don't know how code is really going to work until you try it for real in the production environment. After, ideally, you have used your best efforts to make sure the code is good, you're going to need to deploy it, and real life is not like the test system. I've seen many operations that work beautifully in the development environment where there's 100,000 rows in the database, and then time out in production where there's 10 million. Right? That's just one of the natures of having difficulties in deploying a thing for real in production. And you do have to implement your system such that rollback is possible. If the Canary deployment results in changes to the database structure and the database is shared amongst all servers, trying to deploy the change can break old servers and leave a rollback as kind of implausible because of it. Let's also talk about containers, because I touched on this already a little bit, but we haven't actually really gone into it at all. So before we do that, I mean, containers are sort of referencing the idea of shipping containers as seen here. But let's talk about how we got here first. In the beginning, yes, this sounds like ancient history. Back in my day, sunny, uphill both ways in the snow. But when you installed a service, you would install and configure the thing by hand, right? There was eventually package managers, but at some point it was like you download the source file and you compile it, and then you edit the configuration file in your editor, and then you run it. Okay. Not always great, making and installing the software didn't always work the way that you expected, but it's okay because package managers were invented. And package managers really help because they deliver to you, a version of the package that you need, and it also has a list of dependencies, so it knows, okay, to install this web server we need the XML parser, and that's pretty good. And the package also includes a script to install it and set it up. You may need to edit it a little bit, but such is life. But if you install multiple services on the same machine, you don't get isolation, and you might have incompatible versions of dependencies. This project needs version 7 of the XML parser, and the other one needs version 6 of the XML parser, and they're not compatible, and you can't have both. This is sometimes referred to as RPM hell, or jar hell, or class loader hell, or DLL hell if it's Windows. So yeah, we don't like that. So okay, one thing that we probably talked about if you took an operating systems course, at least with me, was this idea of virtual machines. And a virtual machine is exactly what it sounds like. It is sort of a simulation of an actual machine. And you configure the VM parameters, you install the guest operating system, and you set it up, and you can copy paste the initial image, which really helps. But for every application, you have a guest operating system running underneath. But that feels like kind of a real headache because, well, why do we have to install the same security patch 10 times? And how much overhead are we losing by running these guest operating systems when we would actually like to see everything running on just one operating system? And that leads us to containers. And containerization gives us many of the advantages of the separation, but without so much overhead, both in terms of maintenance and runtime cost of the guest operating system. Containers are run by a container engine, so there's some abstraction of the underlying hardware, and the container is assembled from a specification that says what libraries, tools, etc. are needed. And so we can see, on the left here, a diagram that shows, virtual machine where you have the guest operating system and everything sort of built on top of the hypervisor above the infrastructure, whereas with the containers, the container engine runs alongside the operating system, and the applications can just run as is. So you can think of a container as being sort of a very lightweight virtual machine. So that is kind of helpful. The goal of your build process is most likely to produce a container such that the container is ready to be deployed and managed by other parts of your infrastructure, like Kubernetes or something else that we talked about earlier. Containers do, however, come with some downsides of just like letting you not upgrade things. Whereas before, if you installed, the operating system patches, you get updates in your shared libraries, but containers allow you to keep old, insecure versions of things around forever, even if the operating system has installed the patch. The things in your libraries in a container for, say, app 3 are still the old ones with the vulnerability, so you might actually be unhappy with that. So don't do that. Keeping on top of security updates is important. This is also automatable. There exist various tools for that, and actually, we should take a minute to talk about that a little bit in our next course topic. So for our next course topic, we're going to look at the actual operations, like keeping things running once we have built things using a good infrastructure, building a good basis, and that will be our last topic for the term.